Hellorld and welcome back. And if you've been following the channel for a long time, me opening the video by saying Hellorld may have caused your ears to perk up. However, if you're not familiar with our older videos, you may be going, what on earth is Hellorld? That sounds ridiculous. Well, you've actually probably seen it a lot in my videos because it's on almost all of my Centurion specific t-shirts. This one has it on it. It says Hellorld and it's preceded by a strange collection of hexadecimal. So what on earth is all of this about? Well, in order to understand this fully, we got to go way back in time. When I first got the Centurion, it was a basket case. It was in very rough shape. It only came with one Hawk drive and it had a Phoenix drive as well. And it had a full complement of cards, but they were all not in great shape. So we did a lot of work and managed to get all of the computer cards up and running, and we were able to confirm that they were working because we were getting to a D equals prompt. But the Hawk drive, which contained the operating system and all of the software on it, was dead. It was very destroyed. The removable platter heads were ripped in half. It looks like somebody tried to remove the removable platter while the heads were still loaded and it was spinning. Even today, sitting here in this room, we have two functioning Hawk drives, but neither of them are the Hawk drive that came with the system originally. That's still this one over here, and it's been relegated to a parts drive to keep these other two up and going. So we found ourselves in this interesting predicament. At the time, I only had the single Hawk drive and the Phoenix, both of which were crashed and not functioning. So I had this computer with nothing to do, and that was where Ken Romaine swooped in and saved the day. And he did so with this little card right here. This is a diagnostic card. They only made about 50 of these and they were not for sale. They were made specifically for Centurion technicians to diagnose broken machines in the field. And this was Ken's personal card. He donated this to this Centurion and it's gotten a lot of great use. And Ken, thank you so much for this. But the reason that this is so pivotal is that here on these 4 ROMs, it contains a collection of diagnostic tests. And these are pretty simple ones at first, a simple multiplexer test, a couple of Hawk tests. But when you get deeper into the tests, you come across something that they call TOS, or Test Operating System. It sounds fancy, but it's really just a memory monitor. Now, what a memory monitor is it allows you to select a certain location in memory and then change the value of data stored at that location. And then tell the memory monitor program to go to that location and start executing those values as if though they were CPU instructions. So there were some really interesting, tricky things that we started to learn by digging through the ROMs. And one of those tricky things was that we discovered where the subroutine to write ASCII data to the terminal was located. So a very smart member of the Discord sent me a collection of hexadecimal values and said, hey, punch this into TOS and see what happens. So I started punching it in and I was looking down and looking back up, and I mean, it's all just pure hex to me. And at that time, I didn't understand any of it. So I punched it in, I told it to go to that location and execute, and it printed Hellorld on the screen. It was supposed to print Hello World, but hello ends in an O and world has an O in the middle of it. So when I was punching in the hexadecimal, I got to that O, punched it in, and when I looked back, I picked up at the O in world. So I had unknowingly skipped space W and then that second O. So we ended up getting Hellorld on the screen, which I find hilarious because the first new software that was written for this machine in like 30 years had a bug in it, and it was something as simple as Hello World. I think it's a hilarious story, and we commemorated it by putting it onto a bunch of t-shirts, and I absolutely love this t-shirt because it always gets people scratching their heads. But Hellorld kind of took on a life of its own. People were sending me really cool photos of them running custom Hellorld programs on their really unique machines, and it just really inspired me to want to revisit Hellorld and explain the code that we ran in much more detail now that I understand it a little better, and maybe try to improve upon it. So the code itself is really simple. We start with an M1000. This is how you tell the memory monitor, TOS, that you want to modify the value in a specific location. And so the code is just really, it's pretty simple. So we'll start with a 7-9. This is a jump subroutine instruction, and the CPU will look at the next 2 bytes after that value for the memory address. That address being 8623. Now that location is actually here on the diag card. These ROMs fill up a specific part of the memory address, and within these ROMs there is a specific location, 8623, where a write string subroutine is located. So all we're doing is borrowing a write string subroutine that was already written for us. Then the next collection of ASCII from C8 to 00 is just the ASCII for Hellorld in all capital letters. And then 00 is a null terminator that the write string subroutine is looking for. And then finally, 7-1 is a jump instruction, and it jumps directly to the address 8001, which is the beginning of the diagnostic ROMs on the diag board here. We really should have been jumping to 864F, which would have got us back to the test operating system, but either way, it worked out just fine. So it was incredibly pivotal to the evolution of this machine. It felt like we hit a proper turning point when we did this, but I think we can do better. So I've been going a little crazy trying to figure out how to write real assembly for this machine lately, and this felt like an excellent time to revisit the Hellorld program and write it as a completely standalone thing, something that doesn't require the diagnostic card to be in there. And I think I've come up with it. So let's spin up the big boy here, get into the operating system, and write our new assembly program. All right, we got the Hawk spun up. We're fully into the operating system. Let's go ahead and write our assembly program. And so I'm going to do that with s.ced here, and we're going to call the name of the program Z Hellorld. We're going to put it on platter 1, and we'll make sure our output device is CRT0. We don't want to put it in any library, and it's not there, so we are going to create it. So we'll hit yes on that. There we go. We're at the main prompt for our text editor here. We'll do an append with A. So we'll start with 10 spaces. And then we'll type title, and then we'll call it Hellorld. The labels are going to live on the far left. We'll call it Z Hellorld. And then we'll do a begin at X 1000. This tells the assembler where this program is going to live in memory. So the next label we're going to do is called entry. And at entry, we're going to do a JSR, which is a jump subroutine. And we're going to tell it to jump to the subroutine called print null. That's the name of our print string subroutine. On the next one, we're going to do a DW. Now this is a really interesting opcode because it's not actually an opcode. It stands for define word. All it's doing is just laying down whatever word I put here at this location in memory. So the word that we're going to lay down here is hexadecimal 8D8A. 8D8A is our new line carriage return characters that we send out to create a new line and make a carriage return. Next, we want to define Hellorld. We just do a define character, and then we space on over here, and we just type Hellorld. The assembler automatically converts that to hexadecimal for us, so we don't need to do that mental conversion for us. And then finally, we just need to define a byte of 0. That's our null terminator. So that's how the print string subroutine knows that we're finished. Now, next we're going to go to the print null subroutine, and we're going to start with a LDAB equals. This is a load A register byte with a direct value, and we're going to make that direct value actually a binary value. So we're going to denote that with a B here, and we're going to make that value 0, 0, 0, 0, 0, 0, 1, 0. That is 8 bits or a full byte. It is the mask to check whether our transmit buffer is empty. We're just loading that up into the A register for a comparison a little later. The next instruction that we're going to do is a XAYB. This is a 1-byte instruction that moves the byte that we just loaded into the A register, that's 000010, into the Y register. Now within the print null subroutine, we want to have kind of a wait loop. So we're going to call that pin loop. And then from here, we're going to do a load B plus. Well, I just made a mistake. I hit the plus on the number pad over here, but that also sends a new line signal as well. This is the benefit of Centurion ED written by Ren. We can actually go back and edit some of this stuff. So pin loop is the name of our loop that we're going to circle around. Load B is loading the B register with a byte. Plus is a indexed load. So this is actually a really smart way that the Centurion is able to pick up those bytes that we laid down. So if we look at the top here, we've got a jump subroutine to print null. The very next byte after that is a define word, which is 8D and then followed by 8A. So when we jump to a subroutine, the return vector from that subroutine is stored in the X register. But we can use this to our advantage because that very next byte after the jump subroutine is one of the first bytes that we want to actually print to the screen. So we read the byte that's stored where the X register is currently pointing, and then we increment that after we're done with it. So it goes to the next byte. And then when we loop around, it goes to the next byte, and then it goes to the next byte, and then it goes to the next byte, until we get to the 00 at the end. Really smart way to abuse the return vector of the jump subroutine to grab some bytes that we just threw up there. Anyways, after we do that, we're gonna do a BZ, which is a branch if 0, over to PNN. Now what this does is it's comparing the B register that we just loaded up in the previous instruction, and it's checking to see if it's 0. If it is 0, we've hit our null terminator, and it's time to jump to the end. We're gonna return out of the subroutine, and we'll be all finished. And the next instruction, we'll do pn wait here, and then we're gonna do a load a byte with a slash here. So we're gonna load whatever value is stored at a specific memory location. And that memory location in this case is XF200. And F200 is the MMIO address of the multiplexer card. And it just so happens that that is the status register. And so now we want to compare whatever we just loaded into the A register with our mask that we stored in the Y register. So we'll do and B, and the 2 bytes that we want to AND together are YL and AL. After that, we want to do another branch, so we'll go branch if 0, and then we're going to branch out to pn wait. So if the transmit buffer is not empty, so we're going to circle back up to pn wait until we get a 0 out of the multiplexer card. So we're going to do a stbb slash. So we're going to store the B register byte, and we're going to store it in the direct location of XF201. This is the MMIO address of the multiplexer card to receive a byte to transmit out to the CRT. Once we store that in there, we are going to jump all the way back up to pn loop here. And then we finish. It's time to get to the end. So we do pn end here. And we're just going to do an RSR, which is a return subroutine. Returns all the way back up to the end of print null. And then we're just going to do end entry here. It's just a little bit of code there to tell us that our program is finished. And that should be everything. So let's list it out. We want to list all lines of it. And it looks like I got a little bit of spacing wrong on the one that we redid, but I think that's going to be okay. So we'll quit out of this. And now let's try to compile it. We'll do a .p.asm, And then we'll do Hellorld. It automatically prepends the Z, so we don't need to worry about that. That's on platter 1. We want our output to be our CRT0, and then we'll just do an X in the end there. And that should go. Let's see if it works. Errors 0, error 0, that's good news. .new x Hellorld, that's making our new executable file there. Yeah, all right, so let's give this a test, but we can't test it from in here. If I do a .run x Hellorld, yeah, see, we get a program malfunction because we didn't program it to run within the operating system. So we got to run it bare metal. We can do that by pressing the select button on the front, type H1 here. This will get us to a name equals prompt. This is a really nice bare metal loader that Centurion included. So we can do x Hellorld. It's on disk 1. The code is nothing. There we go. Hellorld, we printed to the screen. So there we go. There's our new Hellorld on the Centurion. What else can we run Hellorld on? Let's write Hellorld on another machine out here. This is exciting. Let's do some more stuff. This is cool. All right, this is my probably favorite microcomputer ever, my TI-99-4. Not a 4A, a legitimate 4 with the awful chiclet keyboard and the almost unusable 9918. It is the real deal original. Pretty rare. They only made about 20,000 of these, and this one works absolutely fantastically. We did go through and fully restore this one, get it up and going, but we had a massive video problem going on. But as you can see, that has since been repaired. What happened was we had a couple of bad 3904s, but originally it had A5T 3904s, and I put in some 2-in 3904s, and the collector and emitter are in different locations on those two different types of transistors. So I desoldered them, flipped them around, soldered them back in, and we got a fully working TI-99-4 now. So let's punch in a Hellorld program on this. So if we just do enter, go to TI Basic, we'll do a print space Hellorld. There we go. We printed Hellorld. That was super boring. That was really not exciting at all. Basic is cheating. I don't like basic. We're not going to use basic. We got to do this the real way. So I'll reset the system here. Get back up to our main screen here. I have a little cartridge in here called mini memory, and that gives us these extra options. Easy bug is the option that we're looking for. So I'll hit number 3. It's going to bring up a little screen here, and it's a memory monitor. It says M is to modify CPU memory, G is modify GROM memory, V is modify VDP memory, so on and so forth. E is to execute our assembly program. So let's start modifying memory. So if we hit enter, got a little question mark here. So we'll start with an M, and we want to modify a certain place in memory, and I actually have gone through and figured out all of this using the help of the very smart people over on the Atari Age forums, Greg and Tercy and all these guys. They taught me a ton about TI-99 stuff, and I'm going to put some of that knowledge to use here today, hopefully. So we're going to start at the memory address 7D00, and if I hit enter, it shows here 04. And it has a little arrow, so I can now start modifying this. And we want to put in certain values here, and we can only really do one at a time. So we'll start with 02, enter, E0, enter, 70, enter, B8. Now the first thing to remember is that this is a full-on 16-bit machine. We have a 16-bit memory address and we have a 16-bit data bus. So the first instruction is a 02E0. This is a what they call LWPI, stands for Load Workspace Pointer Immediate. And we're loading that with 70B8. This is essentially telling the program where the registers are. There are 16 workspace registers in this machine, R0 through R16, and they're located at 70B8 and on. So next we'll do a 04C0, and this is a clear register 0. Essentially, we're setting register 0 to all zeros. Next, we're going to do a 02, 01, 2000. And then this is a load immediate into register 1. And we're going to load register 1 with the hexadecimal value 2000. And then we're going to follow that up with a 0420 6024. Now this is a branch and load workspace pointer, and I don't really know what this means. I think it has something to do with jumping to a subroutine or a program that's not covered within our original workspace. All I know is that the manual told me to use this when I wanted to print something to the screen. This could be due to the fact that there is a very strange video setup going on here with the VDP and the RAM and all of that stuff. But the manual says when writing assembly to do a BLWP and do it to this. So that's what I did, and I think it should work. The next one is going to be 0580. And this is to increment register 0. So register 0 we cleared to 0, now we're incrementing it to 1. And then we're going to follow that up with a 0280 0300. Now what this is doing is it's comparing register 0 with the decimal value 768, which I think in hexadecimal is 0300. There are 767 locations on the screen where we can put the cursor, and so we're comparing R0 to if we are off the screen. So this is a little loop that we're running to print something to every location on the screen. And what we're printing is R1 that we loaded with the hexadecimal 2000, which just so happens to be the character for space. So all we're doing is clearing the screen with this little loop right here. And to finish it off, we're going to do a 11 and then FA. This is a jump if less than, I believe. That's what the 11 is. Essentially what it's doing is it's looking at the previous instruction, which was the compare. And if the value of that compare is less than 0, we haven't gotten to 768 yet. So we're going to loop back around up to our little loop that is incrementing and printing a space to the screen to clear the screen. And the number of bytes that we're looping back is denoted by FAs. So the next instruction that we're going to do is a 0200 012A. This is a load immediate into register 0, and we're loading that immediate value of 012A, or 298 in decibel. Essentially this is telling us where we're going to print on the screen. 298 just so happens to be dead square in the middle of the screen. So the next one is another load immediate. We're going to do a 0201, and then we're going to follow that up with a 7D28. This is loading R1 with the immediate value of where our bytes that contain the text that we want to print are located at. And those bytes are located at 7D28. 7D28 is all the way at the end. So we put our Hellorld text all the way at the bottom. We'll get to typing that in a little later. So after we do that, we need to tell it how many bytes to read in. So we'll follow that up with a 02020009. And this is another load immediate, and we're loading the register 2 with the value of 9, which is how many bytes that we need it to read to print to the screen. So that's pretty easy. Now we need to tell it to just do the print, which is 04206028. That is our branch with workspace pointer that's going off and and doing its magic. And then now we need to wrap the program up. So we're going to do a 10FE. Essentially, I think this is telling it to jump 1 byte backwards. So it's just going to constantly jump back to the instruction that says jump. So we just create a little infinite loop that creates the machine to just sit there and do nothing. This is equivalent to halting the CPU. And then finally, we got to fill out the text for Hellorld. And I think that's everything. I've made a couple of typos here that I sliced out in editing, which is why the screen always looks a little different every time I cut back to this camera over here. But I'm going to go through and double check that I've got all of my raw hexadecimal punched in correctly right quick. Hopefully it's all looking good. So let me run through that right quick. All right, that's all looking good. We're going to do E7D00. What should happen is it should clear the screen and then it should print Hellorld right in the middle. Let's hit that enter key. Yes! Hellorld right in the center of the screen. That is so cool. Oh, I'm so glad that worked. That's awesome. There we go. Hellorld running on two of my favorite machines in the room, the Centurion and the little TI-99-4 here. And man, it was so cool seeing these machines print something to the screen that we wrote in raw hexadecimal or raw assembly. Now, I am absolutely going to catalog this. I have a website that I'm building, a little GitHub wiki. I'll put a link to it in the description below that is going to catalog every instance of Hellorld running on a unique machine. Like I said at the beginning, we've already gotten a ton of excellent submissions. I know that there's a SEL 810A in there, an SWT PC, a whole lot of really cool things running Hellorld, and I want to see more. Send me photos, send me the hexadecimal or the assembly. I'll write up a little blurb about it and we'll get it onto that wiki website and catalog as many unique machines running Hellorld as possible. Now, the keyword there is unique. There's two big caveats that I want to put in here. The first is that, well, we saw that running it in BASIC is awfully boring. So I'm not going to put anything on there that's just running BASIC. That's super easy. Print Hellorld. We want to see it running in raw assembly or pure hexadecimal. I want to see the machine code that gets this machine to print Hellorld to the screen. Also, I do want to kind of limit it to unique machines. If I have 100 different instances of a Commodore 64 running Hellorld in machine code, that's really not that exciting. And actually, I think even the 99.4 here isn't that exciting, but I'm the one building the website, so I'm gonna put it on there. But I wanna see your unique machines, things like PDPs or Zylogs or other mini computers or even homebrews. I love seeing homebrews running Hellorld. There's been a ton of awesome homebrew submissions so far. Those are already up on the website. It's going to be really cool to see even more homebrews running Hellorld. So links in the description below. Hit me up on Discord. Send me pictures. Send me code. We'll update the site and make a catalog of Hellorld. So with that, I'm going to say Hellorld to you all, and I want to thank you so much for watching, and I hope to see you in the next episode.